Hello, everyone. Welcome to the Canadian Electricity Association's Conversation webinar series. I'm Carrie Fournier, Manager of OHS and Standards Programs here at CEA, and I'll be your host for today's webinar. The CEA has worked with our corporate partners to develop this conversation series, which focuses on solutions to current and future challenges faced by our industry. Today, Powell will be presenting arc-resistant switchgear, a practical look. For companies operating in a high-hazard industry, safety is always top of mind. Ensuring increased arc flash hazard protection for personnel operating around the equipment is a commitment and a core value for most organizations as more and more emphasis is placed on personnel safety in the workplace. The potential cost in terms of personnel safety and equipment damage is high when an arcing fault occurs. An explosion due to an arcing occurring within the switchgear causes a significant amount of economic loss due to interruptions of energy distribution and business continuity, as well as the damage of the equipment and the associated components. Many factors influence the equipment performance and many effects from an arc flash that are often overlooked. To obtain the maximum benefits from arc-resistant equipment installation, one must understand how the equipment is tested and evaluated and how this relates to the goals of the Total Safety Program. This presentation will highlight the fundamental purpose of arc-resistant designs and how the equipment works in conjunction with other protective devices to minimize operator exposure to the hazards of an internal arc fault. Before we get started, please feel free to type any questions into the questions panel on the right of your webinar screen. There will be a Q&A at the end of this webinar. We will be emailing the recording of this presentation after the webinar along with a post-webinar survey. We certainly appreciate your feedback. We are also interested in any topics you would like to see as part of this conversation series. Our presenter today is Michael Wachter, PE Technical Director, Corporate Product Development at Powell Industries, Inc. Michael, I'll now turn the webinar over to you.
Thank you. Good morning and good afternoon, depending on which coast you're closer to. I appreciate the opportunity to come in and do a presentation on arc-resistant equipment and what I feel is an essential portion of switchgear and operator safety. And once again, here we go. Today I'm going to cover a brief introduction to arcing faults, how we test, and primarily I'm going to focus on the IEEE testing guide, but I'll point out some things about the CSA Canadian test guide, the original Canadian guide from EMAC, as well as the international guide from the IEC. Then we'll talk about application, which is the thing I think is most important. Workplace safety, coordination of protection, and mitigation techniques. Because what we're really interested in is how do we keep our operators safe? So, having said that, most electrical arcing events occur on low voltage equipment. And whether this is because it's low voltage and we're not afraid of it, or there's more of it and it's a statistical thing, or it's just that it's smaller and it's easier to start an arc, we can debate. But I'm not going to talk much about low voltage today, simply because medium voltage is more dramatic. When you have a failure in medium voltage, there's an explosion, there's fire, things fly. So for the purposes of explaining the catastrophic event that is an arcing fault, I think medium voltage is the best way to go. So we'll focus on that. I am happy to take questions online or offline about low voltage events. All equipment, medium voltage, low voltage, everything is tested. You can't buy equipment that isn't tested, but it's tested for its function. And its function is to protect downstream equipment. To do this, we test with what we call a bolted fault. Literally, we bolt a piece of bus to the equipment at the outgoing terminals and simulate the current load that it would have downstream in the event of a fault downstream. Arcing faults are much different. Arcing faults occur inside of the protective equipment. They are not downstream of the equipment, and they present a different set of hazards to both the equipment and to the operator who might be nearby. We're going to look at a couple of videos now and show the difference between a bolted fault, a failure in the downstream equipment, and an arcing fault, failure in the equipment that is designed to protect. I'm going to show both videos back to back. So the first is the bolted fault. It's a high-speed video shot in black and white. You're looking down into a circuit breaker compartment. There's movement. I assure you this is not the equipment moving, it's the camera, because we suspended it from a crane and the chains were magnetic, so the high current induced some magnetic motion in the camera. The second fault we're going to look at is the same type of fault, but now induced as an arcing fault, and we'll show the differences. As you can see, there's a dramatic difference between those two events. In the first event, all of the energy went into the bus bar and into creating the magnetic field. In the second event, about 50% of the fault energy went into the atmosphere. This is why we're afraid of arcing faults. There's an exposure to the arc flash, that fireball that you saw come out of the top of the equipment. We spend a lot of time and money figuring out how to protect ourselves from that fireball. There's also mechanical stresses caused by the pressure wave. There's an extreme pressure rise inside of the equipment. If you think back to your thermodynamics classes, when you have an event such as an arc, and an electrical arc is about the third hottest event that occurs on the planet Earth, you superheat the surrounding air, it expands. It also vaporizes the surrounding material, and the transition from solid to gas creates a radical change in the volume of the molecules inside the enclosure. And so you wind up with this huge pressure increase. We like to refer to that as a thermoacoustic blast. There's also thermal stresses from the radiated heat. As I said, the arc is the third hottest event on this planet at about 20,000 degrees Kelvin at its roots. By comparison, the surface of the sun is only about 5,000 degrees Kelvin. There's potential contact with energized parts because there is the potential for the equipment to open up and expose the conductors. There's a release of toxic gases. Anything touched by the arc at this temperature is going to be vaporized, and those vapors are going to contain some pretty nasty things. It could be burning paint, it could be molten metal, it could be the gas that's used for insulating the equipment. There are a number of different things but it is a basic toxic combination. And then finally, airborne debris. Anytime you have an explosion of this nature, you're very likely to throw parts in a number of directions. I'm going to show 3 videos now that emphasize this. The first is going to emphasize the pressure wave, the second will emphasize the toxic gas, and the third will emphasize airborne debris. A couple of things that I want to emphasize myself here. When you're looking at the first video, you'll be looking at the end of the switchgear. You'll see a 2x4 stand on the left-hand side. Imagine that you're the operator in front of that equipment where the stand is, and think about how PPE is going to protect you from what you see happen. The second event is a release of toxic gases, and while the gases that are released are intended to go outside of the enclosure in the room, in this case, just imagine what happens if they're not vented outside of the building. And then finally, the airborne debris video shows what happens when a particular metal is struck by the arc and the metal has a low melting point. In this case, it was an aluminum gland plate over a piece of bus duct entry. Okay, hopefully everyone saw those videos. I apologize for the volume on the second one. But that also sort of emphasizes the level of sound pressure that occurs in an arcing fault. We've measured values as high as 174 dB in a building in an enclosed area. So how do we test? How do we prove that we have a design that can withstand these events? Obviously, those 3 videos were all failures. So what do? Well, we come up with a test guide. As a bit of a history lesson, the first guide came out of the European community in the IEC. It was originally IEC document 298 with Appendix A. This is now IEC 62271-200, Annex A. In the IEC world, medium voltage equipment does not have to be insulated in the same way that you're probably used to with metal-clad switchgear in North America. You can have a completely uninsulated run of bus. You don't have to compartmentalize. Certain interlocks to prevent misoperation are not required. So back in the 70s, they had issues with arcing faults and wrote 298 Appendix or Annex A to address this. They've since come out with a low voltage document, 61641, and made a bunch of improvements to all of these documents since. about 10 years later, EMAC in Canada saw a need for arc protection and addressed it by writing G14-1, released in 1987. Now, this procedure only addressed metal-clad medium voltage switchgear. Metal-clad being the one design that was least likely to have an arc fault, but probably the one that was the most devastating when a fault occurs, because it was compartmentalized and the pressures inside of each compartment became much higher, much smaller area to vent the gas, and so you had a bigger explosion. In the 1990s, the early 1990s, the IEEE began writing C37.20.7. It has undergone a number of iterations. In fact, it is being revised as we speak for, I think, the 5th time, because as we test and as we get better at design, we discover new things to look into. During the process of writing 20.7, the CSA picked up on it and took a draft copy and wrote 22.2, number .22 in 2011, I think it came out. And it included some of the equipment that was missing from the IEEE version, the EMAC, and the IEC versions, which all dealt with medium voltage switchgear, or in the case of the IEEE, low voltage switchgear. It didn't deal with motor control, which was of interest to the Canadian users, and so the CSA document wrote in that section. Now we're to a point where the IEEE, I think, is the most comprehensive of all of the test guides. I'm particularly proud of it because I've been the chair of it since its inception. I finally stepped down this year. It now includes all of the items that you see in red. So not only does it pick up the big 3 of low voltage and medium voltage switchgear, it picks up outdoor equipment, medium and low voltage motor control, switchboards, metal enclosed bus, and GIS equipment, gas insulated switchgear. No other document covers all of these types of equipment. So let's look at ratings. How do we know what we're getting and what it's going to do for us? Well, basically, what's important to us when we're looking at arc resistant equipment is, where's the protection going to be? We call that accessibility type. That tells you what areas, what surfaces on the equipment are going to offer arc fault protection. Then we want to know, well, what's the most current? What's the biggest fault the equipment can handle? Well, that's the arcing current, or the rated internal arcing short circuit current. And then we need to know how long it's protected for, because we need to coordinate our other protection. And we find that value in the arcing duration. These are the IEEE ratings, the accessibility type. You'll find that these pretty much match exactly the CSA document, with the exception of the last suffix item. There's good coordination between CSA and the IEEE. So generally speaking, when I'm talking about the IEEE, I'm also talking about CSA. Type 1 is equipment that's protected in the front only. This is a holdover from EMAC. You don't see a lot of equipment protected front only, but there are reasons for doing it economically when the equipment is not accessible except in the front. Most people are looking at type 2 equipment, which is offering arc protection in the front, back, and sides up to a height of 2 meters. Now, in addition to these base ratings, We offer suffix ratings, which are enhancements. These enhancements are protected in an instrument compartment, so the operator can open the low voltage compartment without having to shut down the gear. The Canadian members of the IEEE wanted something that was the equivalent to the old EMAC Type C equipment. So we added in suffix C, which is protection from compartment to compartment. And then with the addition of bus duct, we had to add in an individual side rating, because with bus duct, you have to know where it's going to vent in order to know how to mount it. So if you think about it, C is for compartment, D is for duct. It just happened to work out that way. Makes us look like we're smarter than we are. All of the test guides have a recommended or a preferred fault level. That fault level is the rated short circuit current of the equipment. In some cases, there is equipment that does not have a short time current, which is the current that we would use to coordinate our protection. And so there is some difference in the rated or preferred duration for that equipment, but the fault current level is pretty much the short circuit level. You can also make an argument that less than the rated short circuit level is an acceptable value, because you've analyzed the circuit and you know that you've got the appropriate coverage. Now, in the IEEE and the CSA document, we have a rated or a preferred arcing duration of ½ second. Like I said, there's low voltage equipment that doesn't have a short time rating, so expecting it to operate for ½ second is unrealistic. And so the preferred duration for these devices is 0.1 second. By contrast, the IEC recommends that you test it for the anticipated requirement. So whatever your protective scheme is going to need is what you would test it to, and it gives a range between 0.1 seconds and 1 second. The old EMAC document required 1 second broken down into 2 different tests, which made for a very unrealistic test procedure. And I won't go into the details, but I'm happy to discuss why offline. The nameplate gives the obvious information of accessibility type and any applicable suffix, the short circuit current rating, and the arcing duration. But there's been the introduction now of protective devices so that you can attain arc resistant protection without necessarily building a piece of robust equipment. These fast acting devices need to be called out on the nameplate. So if you're using a device for your protection, we mark the nameplate with the type of protective device. If you're looking at devices that are designed to prevent the arc from sustaining, we also have a rating now that is self-extinguishing, and a time is required for how long the gear can endure the fault before the fault goes out, and that helps you coordinate all of your protection. For an evaluation, all of the guides are exactly the same. This is the way we try to analyze the effects of the fault and the hazard presented to the operator. They don't cover everything, but this is what they do cover. Doors and latches are latched, secured. Covers don't open. So if you close the door and latch the door, you don't expect it to open back up. No fragmentation of the equipment. And simply what that means is the gear doesn't blow apart. It doesn't blow things out of it that could be hazardous. The limit on what can be ejected is 60 grams. That's roughly the mass of a 2-inch long 3/8 bolt. The arcing can't burn holes in the equipment, and it doesn't matter whether gas, smoke is ejected from the hole. It cannot burn a hole in the equipment, period. That is an instant failure. We surround the gear with burn indicators to monitor escaping gas and radiated heat. In the case of the IEEE and the CSA document, we have a particular type of cotton. It has no flame retardant chemical treatment. It's set at a certain distance from the equipment. If you burn an indicator, you fail the test. A point to keep in mind is that the distance from the surface of the equipment to those burn indicators is different in the IEEE and CSA than the value that you test in the IEC world. Now, whether this makes a difference is a debatable issue, but they are different. The final difference and the final evaluation criteria is the ground connection must remain effective. Unfortunately, there's some disagreement between the IEEE and the IEC on how to ground the test sample. And the CSA document accepts either methodology. So my word of caution here is be very, very cognizant of how the equipment was tested and how it will be grounded in the field, because you may be surprised if you have an event and the grounds are different. The application of the equipment is where the rubber really hits the road. How am I going to make my working environment safe? We've got safety documents. In the United States, it's NFPA 70E. In Canada, it's Z462. These documents analyze the at-risk procedures used by operators. It doesn't tell you a particular rating of equipment. It just analyzes the activity and the type of equipment and the amount of risk that you're engaging in, and makes recommendations for PPE based on that activity level and the energy that could be released by a fault. The calculation of the fault energy or the incident energy comes from IEEE 1584. And what I'd like to point out here is very, very important. 1584 is a mathematical calculation. It does not take into account arc resistant equipment, creating a barrier between the event and the operator. So the incident energy that you calculate for standard switchgear could be the same as the incident energy you calculate for arc resistant gear. And in one case, the operator is in extreme danger, and in the other case, may not be in so much danger. The reason for this is the barrier that the arc resistant gear creates. There is no reduction in the incident energy. There is only a reduction in the risk of exposure. One other thing I'd like to point out when we're looking at application is the large installed base of non-arc resistant equipment. As we get better in the electrical industry creating sensing devices and fast acting trip and commutating devices, there's a tendency to believe that you can take this old equipment and retrofit it with these new devices and create an arc resistant piece of equipment. The answer to that question is no, you can't create an arc resistant piece of equipment unless you have tested it to an arc resistant test guide. You can improve the behavior, but you can't just call it arc resistant without having performed a test to prove the equipment will offer the arc resistant protection. Now, if we look at the coordination of protection, remember that the power transfer, the amount of energy that the operator is exposed to, is about 50% of the available energy in the fault when there's an arcing fault. And this is really important. When it's a bolted fault, a downstream fault, the equipment absorbs 100% of the energy. When it's an arcing fault, about 50% of that energy gets released into the atmosphere and the operator is now exposed. This is a typical test result showing current and voltage waveforms. What I'd like to point out here is if you look at the very top trace, channel 1, that first loop of current, that's the peak. That is the highest amount of current that the short circuit produces. And I've drawn a line from the center of that peak down to the bottom of the screen where there are two waveforms that represent the pressure around the arc. Pressure transducers, the bottom one being very close to the arc and the top one being where the pressure relief venting on this piece of equipment was located. If we zoom in, we can see the time lag between the peak current and the peak pressure is about 4 milliseconds. And that's important because what that means is from the start of the event until the point where the gear starts to come apart, or as we affectionately refer to it, spontaneously disassembles, you're looking at about 3/4 of a cycle, 10 to 12 milliseconds, typically. You'll notice that the bottom trace close to the arc and the trace above it close to the vent have a little bit of a time delay between the two of them. Basically, the pressure wave moves through the equipment at the speed of sound. And so to travel from the bottom of the equipment on the bus to a vent at the top of the equipment, you get a little bit of a time delay. You get a little bit of change in pressure. And then what you'll see afterwards is an oscillating pressure where it heats up, it vents, it heats up, it vents. You can't really see that in a video. It's happening too quickly, but graphically it does show up. Now, if we look at this in a representation of current, pressure, and how the arc is behaving in a classic sense, there are 4 stages of an arc fault. Effectively, what you have is shortly after the peak of the first current loop, the pressure hits its maximum, and we call that the compression phase. After the compression phase or compression stage, the equipment starts to leak pressure, either through intentional means like a pressure relief opening or unintentional means like the door coming off or the side sheet splitting or something that is completely uncontrolled. Keep this graph in mind now as we look at mitigation techniques. How do we get the equipment to behave the way we want it to behave in conjunction with the protective devices that we would like to use? Well, let's start out by saying that in all traditional relaying schemes, we require some type of sensor and some type of interrupting device, and they require time to operate. If we move to arc mitigation devices that are specific to arc mitigation, we still require sensors and an interrupting or commutating device and time for these devices to operate. Now, what you have to be aware of is that the coordination between the equipment's mechanical capability and the speed of the protective device is what makes the difference between equipment exploding and equipment shutting down in an orderly fashion. The most effective methodology for mitigating arc faults shows up in low voltage equipment primarily. Current limiting, fast acting fuses, and fast acting circuit breakers. These will operate typically in a quarter cycle when they're in current limiting mode. This is great. This happens long before we reach the peak current, long before we reach the peak pressure. Unfortunately, they're not always available at every voltage level and at every current level we need. For example, in motor control, at 5 kV, a 400 amp fuse is readily available at 63 kA fault current. It is not readily available at an 800 amp fuse level for 63 kA. 50 kA is readily available, but if you're connected to equipment that's rated at 63, 50 kA may not be sufficient to interrupt the fault. So you have to examine these sorts of things. Fuses are great, but they're not the answer to everything. Same with fast-acting breakers. They work pretty much the same way. The other thing you have to concern yourself with is when you're not at the peak current, when you're outside of current limiting mode, how long will you allow the fault to burn before the protective device operates? This could be long enough to damage the equipment and have the fault get outside of the boundaries of the equipment. In the area of specialty equipment for arcing, there are light sensors, pressure sensors, and sound devices. And these all, again, require a device to interrupt or shunt the current. They don't deal with the problem themselves. They are just the sensing devices. And you see some incredibly fast numbers here. You see relays that can make decisions in nanoseconds. The problem is they're operating circuit breakers or other devices that operate in milliseconds. Now, there are other devices that operate much faster than circuit breakers. These are crowbar devices, fast-acting ground switches, things that intentionally short out the bus. They put a bolted fault effectively or a ground fault on the equipment. This is brilliant when it comes to personnel protection. This pulls all the energy away from the arcing fault and renders it inert. It's great, but it has the possibility of undesirable effects on the equipment tied downstream, particularly wound equipment like transformers and motors. You've got very small wire with very small levels of insulation packed very closely together. When you go from an arcing fault to a bolted fault, you double the energy seen by the bus. So there's a very abrupt change in the magnetic forces. These pieces of equipment that are wound are not designed to withstand momentary forces of that level. Additionally, all of these special sensors have typically multiple levels or multiple layers of logic involved to determine the fault. It turns out in the original version of the light sensor that when an operator would open the back door to do an infrared scan of the bus, the light in the room would shine in on the sensor and trip the equipment because it couldn't determine whether it was the fluorescent light overhead or the light from an arc fault. We've gotten a lot better at those sensors now, but most of this equipment also includes some sort of current discrimination level of logic to make sure that we truly have a fault. There are other devices known as shunting or commutating devices where you can transfer the arc from an uncontrolled point on the bus to a controlled device mounted somewhere in the equipment. The cautionary tale there is that you need to make sure the impedance between the source and the device is lower than the impedance between the source and the fault. Otherwise, it won't transfer. Arcs don't exist in parallel. So to get this to work, you basically have to shut down your entire bus, which means that these devices have to be located at or near the incoming breaker. The final method that I'd like to talk about primarily is used in low voltage equipment, and that's resistance grounding. It limits the ground fault current, and this has a very pronounced effect on the sustainability of the arc. I don't really have enough data to say that it has the same effect on medium voltage, although I expect that it would make an improvement. But in low voltage, you can all but make the fault disappear by taking away the ground path. And this becomes an important argument when we're looking at the IEC methodology of testing versus the IEEE methodology of testing when it comes to grounding the test sample. So let's summarize by going back to that coordination protection graph. We've got our current wave and our pressure wave and our stages of the arc fault. And if you look at the bar graphs below, there are different types of circuit breakers, different types of switching devices, current limiting fuses, high-speed breakers, high-speed grounding, sensor and relay speeds are all put into this graphic so that you can see there are very, very few methods of mitigating the fault that will take it offline before the critical pressure is reached. And because of that, I make the argument that arc-resistant switchgear in some form or other is absolutely essential to allow your protective device to operate. One other thing that's not covered by the test guides is a plenum or a containment system. What we're looking at here is a way to get the toxic gases, the sound pressure, the falling debris, etc., away from the operator. This is not defined in the test guide. It's not a requirement for arc-resistant equipment. So as a user, you're obligated to ask for it. You can order arc-resistant gear. You may or may not get a plenum or a containment system as part of that. So ask for it. It will benefit you greatly, as you recall from looking at the earlier videos. In conclusion, I'd just like to hit these bullet points. Arc fault protection is a system and not an individual product. You can't buy the magic bead or the silver bullet. It just doesn't work that way. You have to have things working in conjunction with each other. Every mitigating device that's out there offers some benefit. Arc-resistant switchgear works with them so that they can perform their intended duty. Improper coordination of this protection and the arc-resistant gear can fail. Proper functioning protective equipment also may still allow a harmful release of gas during a fault event. It may also allow an injurious level of heat in the area where the operator might be. The burn indicators that we use are generally accepted to ignite at around 4 calories to 4.5 calories per square centimeter. This is greater than a second-degree burn, so that you probably still need to wear PPE even though you're looking at arc-resistant equipment. All right. Not all mitigation techniques work the same, so look at the one that's best for your installation, and remember that retrofitting equipment with these mitigating devices is not as easy as it appears. And with that, I'd like to open the discussion here for questions, and I thank you for your time.
Thank you, Michael. That was a wonderful presentation. I don't think anyone questions the safety hazards of an arc flash. This is extremely important. So like you said, we're now in the Q&A portion of our program. So as a reminder, please use the question panel on the right of your screen to type in any questions that you may have. And we'll start off with the first question, which is, in regards to arc flash relays versus arc resistant switchgear, which one do you believe is safer?
I think you have to use both. And I think that was the major point that I hope to drive home with this presentation, is that the relays are great devices. They operate quickly, but they have to operate a circuit breaker or some other device, which takes more time than the fault is going to allow before the equipment starts to come apart. So in regard to that, I think you have to use both. You have to have some level of mechanical protection, which is the arc resistant switchgear, coupled with these fast acting devices. And it's not a belt and suspenders sort of thing. I think it's essential that you have both working together.
Absolutely, sounds good. So our second question is, does type 2C arc resistant switchgear retain its performance with the door open?
Yes and no. And I don't mean to be facetious there. If you have 2C equipment, and let's say you have a lineup of equipment that is 5 vertical sections, and you've opened the circuit breaker door on section 5, and a fault occurs in the cable compartment of section 2. If it has passed the suffix C test requirements, the operator who is pulling the circuit breaker out of section 5 would be protected. Okay. If the fault occurred in section 5, having 2C ratings won't make any difference. It's going to happen right where the operator is. My big concern with 2C is that it gives the impression that it's safe to work on energized equipment. I can't, as a manufacturer with a clear conscience, tell you that it's safe to work on energized gear. But in terms of collateral damage, the C suffix protects you. You know, you won't have a fault elsewhere in the gear going into the compartment that you're in. And in that regard, it improves the level of safety tremendously.
Perfect, thank you. Our next question is type 2BC arc resistant switchgear better than 2C? Is 2C better, and what is the difference?
Okay, somebody out there knows me and doesn't like me. The BC suffix was a typographical error in the test guide, and I know that for a fact because I'm the typist. I made the mistake cutting and pasting in one of the original versions of the document. BC is supposed to be identical to C. There is a suffix B and a suffix C. Suffix B has to do with the protection of an instrument compartment. Suffix C has to do with the protection of all compartments, including the B instrument compartment. So if you buy suffix C, you automatically get B protection. I know there were a lot of really clever salesmen who were manipulating the words of the test guide to try to make it seem like there was some difference. It was a typographical error. The 17 edition of 20.7 fixes that problem, and it points out that equipment truly tested in the correct way to the test guide, whether it has BC on the label or C, it is definitely the same equipment. Now, don't let people confuse you and say that it's type 2B in the back, but it's type 2C in the front because they're doing something weird with their exhaust systems. That's not the case. If that would not have passed a suffix C test, even when it was called BC. So like I said, it's a clever marketing scheme that I'm as an engineer not real happy about, and I'm the one that seeded it, unfortunately.
Okay. Well, thank you for that explanation. We do have some more questions coming in.
Okay.
The next one is, do non-arc resistant switchgear with arc mitigation devices like relay with fiber optics perform well in comparison to arc resistant switchgear?
The answer is they can. It depends on the fault level. If the fault is going to last for longer than the gear can hold together, and it occurs in a time frame where the protective device hasn't operated, then the answer is no, the gear is going to come apart. So you just have to look at the timing. That's what those graphics were all about. If you've got a protective device that can take you offline in less than about 10 or 12 milliseconds, then you're good. You probably don't need to worry about arc resistant per se switchgear. But there are very few devices that can do that. There are a lot who claim they can, but the reality is that instantaneous is not immediate. Instantaneous has some time.
Okay, perfect. Okay, next question. Can you please highlight or confirm the limitations it can imply if the upstream protection can't operate within the design of 0.5 seconds? Does it mean that our incoming will not be arc resistant?
If the upstream protection cannot operate within the 0.5 second rating of the equipment, then the incoming terminals of that equipment are at risk. The saving grace here is the impedance of the system is going to knock the current down. You're not going to see as catastrophic a fault as what I showed you in the videos. But yes, if your upstream equipment operates because of coordination slower than half a second, and you only have a half-second rated piece of equipment, you may not be completely protected.
Perfect, thank you. Our next question, type 2B or type 2C is what industry uses for MV switchgear. Type 2 applies to the front, back, and sides of switchgear, and I'd like to know how we deal with top and bottom of the switchgear. For example, say cable entry, bus duct on top and bottom cable entry. What does the standard cover on this, and do we need to use special cable gland?
As far as the bottom of the equipment, there is absolutely no guidance given. You are at the mercy of the switchgear manufacturer to give you guidance, and all of the major manufacturers that I'm familiar with, even the smaller manufacturers that I'm familiar with, understand the risks of placing arc-resistant equipment over a cable vault, and will make recommendations about how to make the penetrations so that you don't blow the fault gases into a vault. From the top, the same basic requirements are there, and you're to a certain degree at the mercy of the manufacturer to give you guidance. But you also have built into the test procedure the requirement for monitoring reflected gas. So if you're going to put a bus duct over the equipment and it might in some way, shape, or form impede the flow of gas out of the equipment, or it might itself fail, then you're obligated to put in a fake ceiling and walls in the test setup in order to measure reflected gases. And your burn indicators are both horizontal and vertical. The horizontal indicators will catch that reflected gas and burn if they're of a sufficient temperature to be injurious. So it's covered a little bit, but not directly.
Perfect. Can you please elaborate a little more on the containment option associated with their equipment?
Containment's an interesting thing because if you calculate up the pressures from a fault in a reasonable duration, you wind up with switchgear that's made out of inch-thick plate and seam welded in order to keep from blowing apart, and that's just not practical. What I've seen our customers do is put a plenum and an exhaust duct over the equipment to guide and direct the byproducts, the fault gases, into an area of a controlled volume where it can expand and cool and then slowly be vented out into another area. So it's just a series of successive pressure relief areas where you're going to larger and larger volumes and letting the gas cool along the way until it's harmless. And that's containment in the version that I've seen. Actually building gear that holds the fault inside would require a really, really fast acting protective system. And then you could contain it because you won't be building up any pressure.
Perfect. We do have a little bit more time. We have some more questions.
Okay.
What are the ranges for the low, medium, and high voltage categories mentioned during presentation?
The ranges, okay. Low voltage typically is from 0 to 1054 volts, but we're talking about in the AC world 240, 480 volt equipment, topping out at about I think 630 volts, but it goes all the way to 1054. Medium voltage starts at 1000 volts and goes to 100,000 volts, but in reality, no one builds anything over about 38 kV for indoor equipment. So you're looking at 1000 volts up to 38 kV. In the realm of gas insulated equipment, they'll take it up to 54 kV, or 52. Whatever the title of that document is, but it goes up to that level for that type of equipment. From 100 kV up, now you're into the high voltage realm, and then beyond that you get into the ultra high voltage, and those guys are mad scientists, and I won't even comment on that equipment because it's not indoor and it's not arc resistant.
Well, thank you so much, Michael. I think we've kind of run out of time. This was a fantastic presentation. A lot of information, very good information. Anyone who has submitted any questions, we will be addressing them offline. So please, following the webinar, we will make sure that we address them all. I would also like to mention that our next Corporate Partner Conversation Series webinars will be held on December 9th. Complytech will be presenting Rethinking Run Until Failure in OT Environments. And on December 10th, it'll be Itron, who presents Leveraging a Multi-Purpose Network to enable digital utilities and smart cities. All of CEA's future events and webinars can be found in our monthly newsletter, Current Affairs, or you can go to the News and Events section on our website at electricity.ca. Thank you again, everyone, for joining us today. Until next time, have a great and safe day. Bye for now.